So it all started out, way back when. Aristotle claimed things just try to find their zen. Things worked in layers, and fire went up, water went down right into a cup. Then Newton came along to set things straight. His fresh new ideas got a lot of hate. He claimed everything fell at the same rate. It really doesn't matter about the weight. After filling in a scientific cavity, he came up with what he called gravity. Gravity's value is 9.8, and this number we are gonna update. That is the purpose of this lab, and we'll do our best so it isn't drab. Alright, so we're just out here, we're just trying to see if we can catch the boy OT booming, not doing what he's supposed to be doing.
Yo,
Boy.
dude.
Oh, come on.
What
are you doing?
What, bro? I'm
Alright.
editing.
It looks fire, bro.
Just make sure it isn't drab, boy. Just make sure it's not drab.
Promise
No
you,
drab.
this ain't gonna be drab.
Bet.
That'd be the best track of the year, bro.
To figure out the value of our letter G, we've got to make our own little effigy. To start it all off, you'll need a ramp and a nice little area that isn't damp. You'll also need a cart to go in motion, as well as a phone to film the commotion. You'll need two things to angle the ramp. We'll use a chair and not a lamp. The other end will sit on a couch. Be careful with the metal or you'll go ouch. To get a wide variety of results, we'll perform 4 trials like adults. To figure out when it stops and starts, we'll use blue Scotch tape for our marks. The distance between start and stop will be 100 centimeters on the dot.
Hold on.
Beat switch.
Before we get started, we have another task. We have to find the angle that the ramp is at. Next we take the cart and place it on the start.
Place it.
Then we use a phone so that the time is shown. Use another phone, record it in slow-mo. Because our ramp is angled, we treat it like triangle. Alright, so the way that we do the actual experiment itself is gonna look something like this. We'll have a little demonstration later, but it's just gonna kind of be like this. So basically you have your cart, you have it go down the ramp, and because you're trying to find the gravity and you're just trying to find the acceleration downwards, we already got the angle measured and all that stuff, but we need to have a timer right down here, so that way we can see how long it's taking for it to get to the bottom of the ramp. So basically we have, first phone is going to be here, and that's going to be the timer. And then we're going to have another phone that's going to be up here recording in slow motion, basically the trial, so we know when exactly we're going to start and stop what we're doing. So basically we just have it go down here, we start the timer,
Start the camera.
have it come down here,
Slow motion it.
and then after it reaches its 100 centimeter mark, we basically just stop the time, and then we calculate the acceleration. Now we need acceleration. Looking at our data. To use this, use a cool equation, clearly using theta. We got mg sine theta equaling ma. However, mass cancels, isolating a. After simplifying, we are left with g sine theta. This is equivalent to acceleration. To figure out the falling a, we need a different way. As you see this looks different. So now we're gonna analyze it.
Analyze.
X equals 1/2 AT squared. Change it up a little bit. Now look at it. Different. A equals 2x over t squared. Since both of our equations are now equal to a, set them both together and have no delay. G sine of theta is equal to 2x, but 2x isn't by itself, it's over t squared. Since we're trying to find g, we gotta isolate it. Now we're left with 2x in the cockpit. It is on the top with others on the bottom. We got sine of theta times t squared. This new equation allows us to solve a final number that we resolved for our own value of gravity. We studied this with levity. This number is the same one as Newton's, and because of this, you can call us good students. Our final answer was 9.8. So we see that in the end, Newton was straight.
He was right.